Alright, here we are, chapter 7. This is day number 1 on harmonic series, a special series that we'll see for the rest of the year, as well as the integral test. So let's get started. Alright, so how can we know whether there is a convergent limit to the sum given here, right? The sum from 1 to infinity of 1 over n. In other words, how does the sum of 1 over n converge? And how can you know? Well, that's an interesting topic because at this point we know that the limit as n goes to infinity of 1 over n is 0. So the door has been opened. We just have to use some tests. If you did the ratio test, which I would not suggest, but you would end up getting that the limit as n goes to infinity of a sub n plus 1 over a sub n will end up equaling 1, which is inconclusive. So what we do is we employ the integral test. And we're going to talk about the details to the integral test on the next page. So the integral test requires the following criteria. All the terms must be positive. It must be continuous on the interval in which your sum is taking place. And it must be decreasing on that as well. So part A of this down here tells us that if the integral from 1 to infinity of f of x dx is equal to some finite number, some countable number, then the series from n equals 1 to infinity of a sub n would converge. Okay, it doesn't tell us a value. Like, this value is not what it converges to. It just tells us that it converges. Right? And if the integral from 1 to infinity, whatever that lower limit might be, of f of x dx comes out to be some form of infinity, then it just tells us that our sequence or our series would diverge. Okay, so the integral test is powerful, but these three things must be true. So if you see a series that looks like a function you might be able to integrate, that is a dead giveaway. Jump to the integral test and go. Alright, so for example, here we've got this one. This looks like something I could integrate from 2 to infinity, right? I took from 2 to infinity of 2 over n natural log of n dn. Right? If you wanted to, you could write that in terms of x. Totally fine. X natural log of x dx. And I see a u substitution problem. I see u equals natural log of x. I see du equal to 1 over x dx. So I can take the 1 over x dx. That becomes du. I'm going to factor the 2 out in front. So I'm going to go from 2 to infinity of 1 over u du. Therefore, when I integrate, I get 2 times the natural log of u evaluated from 2 to infinity. But recall that u was the natural log of x. So I've got 2 times the natural log of x from 2 to infinity. So I'm going to use improper integrals to evaluate that, which would yield this for me. 2 natural log of the natural log of b minus 2 times the natural log of 2 as b goes to infinity. Well, unfortunately, as b goes to infinity, this term also goes to infinity, and infinity minus some finite value. I got a little crazy there with my natural logs nested, is still going to equal infinity. Therefore, what does that tell us? It tells us that the original series is divergent. It is divergent. A couple other things I want to address. Are the terms positive? Well, natural log n is always positive, and natural log of n will always be positive as long as n is 2 or greater. So we can check that off. Continuous on that domain from 2 to infinity, check. Is f of x decreasing? What you could do is find the derivative of that and show that it's decreasing, kind of like how we did before when we looked at monotonic increasing or decreasing. And in this case, you would find that it's decreasing. You would find that f prime of x would be less than 0 for all values of n greater than or equal to 2. Okay, so that's the integral test. What it does is it takes a series that looks like something we can integrate, and we integrate it. If we get some finite value, then we're good to go, and we've got a convergent series. If we don't, like this case, then it's a divergent series. Let's try another. This one's already laid out. This right here you should see and just immediately think arctangent from 1 to infinity. So I integrate from 1 to infinity. It's continuous, it's positive, and it's decreasing. Therefore, we can use the integral test. If I take the integral of that, I get limit as b goes to infinity of arctan of x from 1 to b. And as b goes to infinity, this thing right here, arctan of b, as b goes to infinity, will go to pi over 2. Right? Recall the graph of arctan. It's got asymptotes at pi over 2 and negative pi over 2. Horizontal asymptotes. Therefore, we can say it's convergent. Right? So since this goes to a finite number, pi over 4, then this will be convergent. To what? We don't know, but we know it's convergent. All right, here is p-series. We see this for the second time. If p, right here, right, so if I have a series from n equals 1 to infinity of 1 over n to some number, right, fill in the blank there. If that number is greater than 1, it will be convergent. If it's less than or equal to 1, it will be divergent. And we see the harmonic series come up here where that value there would be 1. Right? So therefore, that's an example of a divergent series, and it's got a special name. It's called the harmonic series. All right, let's keep moving. Let's look at a homework problem. This one, I would simply, this is divergent, I know that for sure. It's going to be divergent because I can split it up to 2 integrals, 1 over n dn minus the integral from 1 to infinity of 1 over n squared dn. I believe this one will be convergent, but this one will be divergent, and when I take infinity minus some finite value, I'll still get infinity. Okay, now this is not the format you should use, but that's a general breakdown, right? You should go through all the different checkpoints you're supposed to on that and find the actual value here and do the work to find that. You could even at this point say just harmonic series is divergent, therefore, you could go through all the formalities there. Okay, here I would integrate. I would use u substitution. N squared plus 1, so du equals 2n dn. So 1/2 du equals n dn. Right, so then I can integrate this from 1 to infinity. N over n squared plus 1 dn. And you go from there, so you get 1 over, it looks like 1 over u du. 1/2 of that from 1 to infinity. This is divergent, as we know. Well, actually, I'm sorry. This is the natural log of u, and u is n squared plus 1. We've got 1/2 of that. If we evaluate that from 1 to infinity, you're going to see that it'll be divergent. Okay, another u substitution here. That one's pretty straightforward as well. Another u substitution here. If I took the integral from 1 to infinity of natural log of n over n dn. I would set u equal to the natural log of n. du would then be 1 over n dn. So this would be the integral from 1 to infinity of, it looks like u du. And therefore you'd get u squared over 2 from 1 to infinity. Anytime you're getting a natural log, you're probably going to have a divergent sequence or series. Natural log of n squared over 2 evaluated from 1 to infinity. So as I plug these in, these values, I take the limit as n goes to infinity. B goes to infinity of the natural log of b squared over 2 minus the natural log of 1 squared over 2. So the limit as b goes to infinity of that first term will be infinity squared over 2.
Why are you doing that?
I'm just doing some math, buddy. And the second one, natural log of 1 is 0, so that'd be 0 squared over 2. And so infinity squared over 2 is still going to be infinity minus 0. Therefore, we'll get an answer of infinity, and therefore this series will be divergent by the integral test. By the integral test. All right. One more, I think. No, I'm not doing that one. No. How about this one? I would rewrite this term, right? This would be the sum from n equals 1 to infinity of n times e to the negative n. I would do that. I would then take the integral from 1 to infinity of n e to the negative n dn. You could use x as well if you prefer. This would be a integration by parts problem, where that is n, u is n, and du is dn. dv would be e to the negative n dn, and so v would equal negative e to the negative n. So as we evaluate, we've got uv minus integral of v du, right? That's our definition of integration by parts. So that would be n times negative e to the negative n, I'm going to write it like that, minus the integral of v du. So I'm going to bring the negative from negative e to the negative n outside and get that. Of course, this is all going to be evaluated from 1 to infinity. So that'd be negative n over e to the n minus e to the negative n evaluated from 1 to infinity. So I'll take my limit as b goes to infinity of negative n over e to the n minus, watch this, 1 over e to the n from 1 to b. As I plug that in, I'm going to evaluate. Okay, I'd get negative b over e to the b minus 1 over e to the b minus, plug in a 1, get negative 1 over e minus 1 over e. Okay, if I take the limit, I should have wrote limit out here, my bad. Limit as b goes to infinity. If I take the limit, this is going to go to infinity over infinity. So I'd use L'Hopital's rule, okay, which would get me negative 1 over, what would that be, e to the n. Okay, this right here, as b goes to infinity, goes to 0. So the limit as n goes to, or as b goes to infinity, of negative 1 over b minus 0 minus, over here I would have negative 2 over e as b goes to infinity, this would also go to 0, and therefore I would get minus a negative 2 over e, so I get 2 over e. That's a finite value. Therefore, this series converges to what we don't know, but we know it converges by the integral test. That's it. That's integral test and harmonic series. Remember, this is the harmonic series, n equals 1 to infinity of 1 over n, and it is a divergent series always, as long as it's positive. All right, so here we go. We're moving on tomorrow. We'll see you then.